The first talk is entitled Compiling Effect Handlers in Capability Passing Style. This paper will be presented by Philip Schuster, and he will tell us about a language for effect handlers in capability passing style and an implementation of the language as a translation to simply typed lambda calculus in iterated continuation passing style.
Hi, I'm Philip, and I present our ICFP 20 paper, Compiling Effect Handlers in Capability Passing Style. This is joint work with Jonathan Emanuel Brachthäuser and Klaus Ostermann. Effect handlers are great, and more languages are getting support for effect handlers, and more libraries with effect handlers emerge. Still, performance is lacking. So this is about the performance of effect handlers. Now, there are two separate aspects to the performance of effect handlers. One, enabling compile time optimizations, and two, having efficient runtime operations. This work is strictly about the former. Effect handlers allow you to abstract over complex patterns of control flow. Yet, this abstraction comes at a cost. To this end, our first result is a theorem. I read it out for you. Full elimination. The translations of capability abstraction, capability application, do, handle, and so on do not introduce any residual lambda abstractions or applications, except for those in the translation of their subterms. What this means, intuitively, is that we fully eliminate all handler abstraction. Of course, this is only possible under certain conditions, and in the paper we formally state those conditions. When those conditions are met, we guarantee full elimination as per this theorem. A theoretical result is great, but what about practice? Well, we've conducted some benchmarks, and they look generally good. And in one case, for example, versus Coca, we see a speed up of 409x. Whoa! So what do? We define a source language, lambda cap, in explicit capability passing style. And we will see what that is in a moment. We then translate this language to simply type lambda calculus in iterated continuation passing style. We will also see what that is in a moment. This translation specializes effectful functions to the number of handlers they are used under. We then go on to define a second language, lambda 2 cap. It has exactly the same syntax as lambda cap, but a different type system. We go on to define a second translation, this time to two-level lambda calculus. This translation specializes effectful functions to concrete handler implementations. So the important keywords are explicit capability passing style and iterated continuation passing style. Let's look at an example. I'll show you a little magic trick. I'll make all handlers disappear. And this will go in two steps corresponding to the two translations. Now, this is an effectful function, choice, written in our source language, lambda cap. It chooses a number between its argument n and 1. It uses two effects, flip for non-deterministic choice and fail for aborting the current continuation. It is written in explicit capability passing style, which means it explicitly abstracts over capabilities flip and fail, in lowercase here. If the argument n is smaller than 1, we fail, or else we flip a coin, and if the result is true, we return n, or else we recurse and choose a smaller number. Let's look at the handling side. Here, we first install a handler for flip. The handler for flip uses its continuation k twice and appends the result. Then we install a handler for fail, which discards its continuation k and immediately answers with the empty list. Both handlers introduce capabilities, lowercase flip and fail. In the call to choice here, we explicitly pass those capabilities to the effectful function choice. Each handler expects a specific answer type. The handler for flip expects a list because it appends the result of the continuation calls. The handler for fail also happens to expect a list because it immediately answers with the empty list. This is also why we wrap the call to choice into a singleton list. We call the list of answer types from outermost handler to innermost handler the stack shape. Let me illustrate why with a picture. This is the call stack at the call to choice. At the bottom, we have the handler for flip, which expects an answer of type list of int. Above it, we have the handler for fail, which expects also an answer type list of int. And then we have a frame which wraps things into the singleton list. Now, to approximate the shape of this stack, we have the list of answer types. In this case, it's a two-element list. The two elements are list of int and list of int. Because we've created the capability flip at the outer handler in a context with a stack shape with a single element, but want to use it inside of the inner handler, we have to fix a mismatch on the type level here and explicitly lift the capability. Guided by the stack shape, we translate our program to iterated continuation parsing style. It is like ordinary continuation parsing style, but with a twist. So the translation looks like this. We have the effectful function choice, and it abstracts over capabilities flip and fail. This is ordinary lambda abstraction. We then define a recursive function loop in iterated continuation parsing style. This means that it gets one or more continuation arguments. The number of continuation arguments is determined by the number of elements in the stack shape. Because we've used choice here under two handlers, correspondingly, in a stack shape with two elements, it now gets two continuation arguments. Capabilities are ordinary functions also in iterated continuation parsing style. For example, fail here gets two continuation arguments. And also in the rest of the function, for example, in the recursive call to loop, we also supply two continuation arguments. If we look at the handling side, we define capabilities flip and fail. Flip is an iterated CPS, but in a stack shape with a single element and consequently gets a single continuation. Fail is an iterated CPS, but in a stack shape with two elements, so it gets two continuations. Now, we also see that lifting has operational meaning. Because we want to use the flip capability in a context where we supply it with two continuation arguments, we somehow have to fix this mismatch. So we define a new capability, lifted flip, which abstracts over two continuations, composes them, and passes the composition to the capability flip. The call to choice now gets 5 arguments. 2 capabilities, the argument n, and 2 continuations. So far, we've seen our source language, lambda cap, and our translation to simply type lambda calculus in iterated continuation parsing style. We've specialized effectful functions to the number of handlers they are used under. We want to go further and specialize functions to concrete handler implementations. As it happens, this program is also typable under the rules of our second language, lambda 2cap, so we can use our second translation to 2-level lambda calculus. This will specialize effectful functions to concrete handler implementations. It is the same as our first translation, except that we mark some applications and abstractions as static and others as dynamic. Specifically, we mark as static capability abstraction, the use of capabilities, capability definitions, the lifting of capabilities, and passing of capabilities to functions. This program now reduces to this. All handlers are gone. We've specialized the effectful function choice to the concrete handler implementations of flip and fail. We call the result of this specialization choice flip fail. The handler implementations have been inlined into the body of choice, and the continuations have been inlined into the handler implementations. This enables optimizations across effect calls. We are not looking up dynamically any handler implementations, and we're not searching for prompts on the stack or something either. We directly invoke the correct continuation. At the handling side, we see that the result is still in iterated continuation parsing style. This is okay. Now, let's look at those benchmark results again. We've benchmarked against different languages and different systems. The Coca language with effect handlers, an implementation of multi-prompt delimited control in JScheme, and effects as implemented in multi-core OCaml. In all of these, we see significant speedups, sometimes very big. In this benchmark, we see a slight slowdown, but still competitive performance. Interestingly, in the case of JScheme, we don't see a difference between our first translation and our second translation. This is because JScheme does all these reductions for us. We didn't have to extend the JScheme compiler or teach it any new tricks. It's just lambdas, inlining, beta reduction. To wrap up, we've presented a compilation technique for effect handlers. Important concepts are explicit capability passing style and iterated continuation passing style. We are translating to just simply type lambda calculus. We don't need any special runtime system, and we don't need any special optimizations either. We have a theorem that guarantees full elimination under certain conditions, which we formally state in the paper. We have benchmarks, which show good speedups. And right now, we're working on integrating this compilation technique in a new standalone language called Effect. You should go check it out.
If you're interested in effect handlers and the implementation technique of explicitly passing them, we invite you to read our paper. At the HOPE workshop, we will present our new language Effect and discuss its design. In another ICFP talk, our collaborator Ning Ning presents the important missing link between traditional effect handlers and explicitly passing them. And finally, she also presents her Haskell implementation at the Haskell Symposium. See you there.
Thank you, Philip. If you are watching this talk live as an ICFP participant, please look to see if there is a Q&A session available in your time band so that you can discuss this work with the author of the paper.